For part B, Catalina and Daniela must not be seated next to each other, but Alvin and Bobby must still be seated. Okay, so they must still be seated, and C and D must not be seated. So we can do this in two ways. So the first method will be from part A. We found all the ways they can sit together if Alvin and Bobby must be seated together. And then we can count the ways C and D can be together and then subtract that from the total number of ways the 10 children can be arranged, and that'll leave us with the ways that they are not together. Okay, so for this one, if Alvin and Bobby must sit together, we've got two cases to consider. So case one, they are at the ends of a row. Okay, so we'll put that in. So that means, for example, Alvin and Bobby could be there. So we'll go through this step by step. So if they're at the ends of the row, as we've got here on the left, we've got two rows. So that's two ways of arranging them at the ends of the row. And then we've also got two factorial ways to arrange A and B. And then we've got 6 places C and D can sit together. So for example, they could be there. So that's seats 3 and 4, or they could be seats 4 and 5, and so on. And then in row 2, so that's two ways in the first row. In row 2, they could either start here, so like CD, or they could start in seat 2, and so on. So that's 4 ways. So altogether, we would have 6 ways for C and D to be together. And then obviously we can times that by 2 factorial, because C and D, or D and C, that order. Then we have 6 factorial ways for the other remaining students to be seated. And then we're going to times by 2 again, because we only considered the left side, but we could also be on the right side of the row and be at the ends of that row. So they're either at the ends on the left or the ends on the right. Okay, and we can work that out on the calculator. So we'll get the calculator up. Okay, so we had 2 times, or 2 factorial, so that's just 2, and then times the 6, and then times 2 factorial, which is also just 2, and then times 6 factorial, and then times 2 again. We get 69,120. So that'll equal. Okay, so that's case 1, if A and B were at the ends of a row. And now we'll consider case 2, so A and B not at the ends of a row. Okay, so if we picture this, we could put them there. So we've got 2 rows. So we'll start with our 2 again. And then we'll times 2 again, because A and B could either be in seats 2 and 3, or they could also be in seats 3 and 4. So there's 2 ways to put A and B not at the ends of a row, times the 2 rows. And then we'll do our 2 factorial, because 2 ways to arrange A and B. And then if A and B are not at the ends of a row, then we're left with 5 places to put C and D's. So they could either be here, so 1, and then 4 in the second row, 2, or they could start there, 3, 4, 5, like that. So then we've got 5 ways to put C and D together, and then the 2 factorial ways to arrange C and D, so CD or DC, and then we've got the 6 factorial ways to arrange the other students. And we'll get the calculator up again and work that one out. Right, so that is going to be 2 times 2 times 2 factorial, which is just 2, and then times the 5, and then 2 factorial again, which is just 2, and then times the 6 factorial, and we get 57,600. So we'll put that in. Okay, so that's the total number of ways C and D can be together is going to be this. So together for C and D, that's going to be 69,120 plus 57,600. And that is equal to 126,720. And therefore, the total ways of C and D not sitting together, but Alvin and Bobby sitting together, will be the total number of ways that can be arranged with A and B together. So that's 645, 120, and then subtract the ways that C and D can be together, which is 1, 2, 6, 7, 2, 0. And that is going to be equal to 518,400. Okay, so that is the first method. So we looked at all the ways that C and D can be together, and then we had the total number of ways the children can be arranged, and we subtracted the ways that C and D were together to find the number of ways that C and D are not sitting together, with Alvin and Bobby still sitting together. Okay, also for part B, we can look at a different method, which will be directly counting the ways C and D are not sitting together. So we'll write that method up as well. Okay, so we'll do a direct count, and as before, we're still going to have to consider 2 cases. Okay, so we'll drop the 5 seats in the 2 rows. So we're going to have case 1, A and B at ends of a row. So we'll work out all the ways A and B can be at the ends. So it can either be at the left end there or the right end. So that's 2 ways per row times 2 rows. And then there's 2 factorial ways of arranging A and B. So that is 8, 8 ways there. Now, for C and D, they can either be, we can either have at least one of C and D in the same row as A and B. So I can have both of them. That's at least one. That's more than one. So I can have them like that. So that is one way. Okay, so we'll start writing this up. So we can have like this. At least one of C and D in the same row as A and B. Okay, so if they're both going to be in the same row, there's just one way that we can do that without them sitting next to each other. Then if we have one in each row, so say one there and one there, so or we could have that. So there's going to be plus. Well, in row 1, we've got 3 spaces left, and each of those spaces will match with 5 spaces in row 2. Then we times by 2 factorial, because we can swap the C and the D round. So that is altogether going to be 32. So that's the number of positions that we can put C and D not next to each other, with at least one of them in the same row as A and B. We're also going to have to times that by 6 factorial, but we'll do that in a moment because that's the remaining 6 positions can be arranged in 6 factorial ways. Okay, or the other option is both C and D in a different row to A and B. Okay, and look at how we can do that. So basically, if we put one of them in seat 1, I'll just put C now. Then I've got 3 spaces, either 1, 2, 3, for D. So we have 3, but then if I start C in position 2, say there, then there's only going to be 2 spaces left for D, and so on. And then if I put C in the third row, in the third seat, sorry, of that second row, then D has to go in the last seat, so 1. And then as before, we times by 2 factorial, so CD or DC, and that's going to equal to 12. Okay, so now we can work this out. So for A and B at the ends of the row, there was 8 ways, and then we're going to times that by, well, we've got 32 ways that's at least one of C and D in the same row, but then we had to times that by the 6 factorial ways to arrange all the other people, and then plus 12, and also times the 6 factorial ways for all the other people. So we can factor the 6 factorial out, so we get 8 times 6 factorial, and then we're going to get 32 plus 12, which is 44. And we can just work that out on the calculator. So we'll bring the calculator up. So we get 8 times 6 factorial, and then times 44. So that's 253,440. Okay, so that's the first case with A and B at the ends of the row. And then we also have to consider A and B not at the ends of the row. So we'll call that case 2. So A and B not at ends of a row. So we'll draw out our 5 seats again and the 2 rows. So basically A and B can be in seats 2 and 3, or they could also be in seats 3 and 4. We also put them there. So that means there's 2 ways we can put them not at the ends in a row. We've got 2 rows, and then times our 2 factorial ways again. And then we get 8 ways that we can put A and B not at the ends of a row. Okay, and as before, we can consider at least one of C and D in the same row. So, for example, if we put C here, then D has to go there. Okay, so there's only one place for D to go there. Okay, or we could put, say, C in the second position, and D can still go in that final place. So altogether there is 2 ways there. And as before, we could just have one of C and D in each row. So say I put C, we've got 1, 2, 3 places, and then 5 places in row 2. It's going to be 3 times 5. And then we times that by 2 factorial, and we get 34. So that's at least one of C, D in the same row as A and B. Okay, and then also we need to consider C and D not in the same row as A and B. So we'll say not in the same row as A and B. So that's going to be exactly the same as before. So we could either have them in like seats 1, 3, 1, 4, 1, 5, and so on. So that would be the 3 positions if we start C at the left end, or in seat 2, then we've got 2 places left for D, and then just 1 place left, times 2 factorial for swapping C and D around. So that is equal to 12. So the total number of ways here then was going to be the 8 ways we can put A and B not at the end. And then that is going to be multiplied by 34 ways for at least one of C and D in the same row as A, B, and then times the 6 factorial ways of arranging the other people, and then as before the 12 ways, and then the 6 factorial ways. So we can factor that out again. We're going to get 8 times 6 factorial, and that's 34 plus 12. So we get 8 times 6 factorial times 46. And that is going to be equal to, get the calculator up again. So now I get 8 times 6 factorial times 46. So 264960. So we get 264960. And therefore the total ways C and D not sitting together with A and B together is going to be that number we just found before. So that was 253440. 53440, and then plus this one we just got here, so 264960, and we can work that out on the calculator. Okay, so we get was it 253440 plus what we just found, 264960. So 264960. And that is equal to 518,400. So 518,400 ways. And that's exactly what we found before. So that's just an alternate method with a direct count.